Hello, and welcome to the Allergica audio presentation. In the next few minutes, we will discuss how viruses, bacteria, fungi, yeast, and parasites affect human health, and what we can do to protect ourselves from them. This entire project was actually inspired by a phone call I received from my wife when she was visiting her parents several thousand miles away. She told me that our eldest son had suddenly come down with a high fever, sore throat, and swollen glands. She asked me what I thought might be going on. I told her he either had a viral or a bacterial infection, most likely strep throat. She asked if there was any treatment she could get at the health food store, as we don't like giving antibiotics in our family except as a last resort. I told her that in my experience, there was nothing that really worked well for either viruses or bacteria that could be found in health food stores. There were plenty of products that increased the strength of the immune response to infection, but nothing that really directly attacked the infections themselves. Well, why not get something that would increase the strength of his immune system, she asked. Our son had a fine immune system, I assured her, and the presence of whatever infection he had was certainly already stimulating a very powerful immune response. Taking herbal extracts to increase the activity of his immune system would do nothing, as it was already on high alert, churning out antibodies, natural killer cells, white blood cells, and all the assorted immune agents that were appropriate for whatever infection he had. My wife was puzzled. I explained that all the products you find on the shelves of the health food store for colds and the immune system were beneficial to people with weak immune systems to begin with. What our son needed was something that directly attacked the infection itself, not an immune stimulant. If it were a virus, we would simply have to let it run its course, and if it was a bacteria, she would have to decide on whether or not to give our son antibiotics. Well, our son finally got over the infection, but the experience made me determined to create a broad-spectrum antimicrobial. I wanted something that would work regardless of the type of infection. I wanted to create the proverbial one thing that you would take to the deserted island with you. Specifically, I wanted something that went after the infections directly and didn't just stimulate an already stimulated immune system. How could I make such a product? There are literally thousands of different types of bacteria and viruses that make people get sick, and each of them would need to be addressed. I envisioned a mix of hundreds of exotic herbs from around the world, each addressing a different kind of infection. Luckily, the answer was much easier than I thought. It turns out that there is a single ingredient with the ability to directly attack almost every infection known to man, and it's found in the most unlikely of places, the humble raspberry. We'll talk more about what this ingredient is and how it works, but first, let's start with a little biological history lesson. It is currently accepted that man rests firmly at the top of the food chain. Unless we wander into the African jungle to be confronted by a lion, or go swimming in the mid-Atlantic and come face to face with a great white shark, we fear no animal. Even in these cases, we have technology to make us safe. We have guns to shoot lions and steel cages should we wish to get close to a man-eating shark and live to tell the tale. This invulnerability to other life forms is, however, an illusion. There are millions of creatures that have been feeding on us, and often killing us since the dawn of time. I'm speaking, of course, not of large and fearsome beasts with claws and fangs, but the tiniest of God's creatures. I'm talking about viruses, bacteria, fungi, yeasts, and parasites. Throughout human history, we have been at war with these infective microbes. They have colonized us, living in our skin, our lungs, our intestines, and our internal organs. Our bodies have become their homes and their food source. Early man could not attack these tiny creatures the same way he could attack a tiger or a pack of wild dogs. New strategies had to be devised. The discovery of fire and the subsequent cooking of our food was our first technological advance and major victory in our war against microbes. Parasites and bacteria were unable to survive the high temperature of our cooking fires, and so we became somewhat protected against parasitic infections of the intestines and bacteria like E. coli. The next advance was the observation that eating certain plants could help the body rid itself of certain infections. This body of knowledge was first learned by watching what plants sick animals would eat to regain their own health, and represents the true origins of modern medicine. The next advance was the domestication of cats. Cats helped us by hunting down the rats and mice that were attracted to the food and garbage of our settlements. In communities where cats were unknown, rat and mouse populations grew unchecked and were impossible to eradicate. The rats and mice themselves were not the problem. Certainly they were a nuisance, but the real danger they represented came from the infections they carried. In 1347, the Black Plague, a disease carried by rats and mice, killed 1/3 of the population of Europe. Better sanitation, plumbing, and refrigeration were the next major advances in our war against microbes. Piles of garbage in early human settlements attracted swarms of flies and other disease-carrying insects. Instead of human waste and refuse being thrown out of the window onto the streets, indoor plumbing and garbage removal services were instituted. This resulted in a decrease in the number of these disease-carrying insects in and around our homes and places of work. Hot and cold running water made clothes and bedding easier to wash on a more regular basis, minimizing the mites and molds that made our blankets their staging ground for a nightly assault on our skin. Finally, refrigeration, first through the use of river ice, then dry ice, and finally modern refrigeration systems, slowed the growth of mold and bacteria on our food. All of these advances moved us forward. The most recent major advance was, of course, the discovery of antibiotics by Alexander Fleming in 1929. By observing that certain molds killed certain bacteria, he was able to discover penicillin. This led to both a deeper understanding of bacteria in general and also to an entire industry dedicated to searching out new and more effective ways to kill bacteria. We've come a long way in our understanding of microbes and our abilities to deal with them. Modern man lives in a mostly disease-free state. Still, the question remains, can we do better? Can we decrease the number of and severity of childhood infections? Can we prevent or shorten the length of the common cold? Can we rid ourselves of the chronic infections that make their homes in us? Can we finally win the war against microbes that was started so long? Let's look at the different kinds of microbes we face and see what can be done about them. The four major classes of infections are viruses, bacteria, fungi and yeast, and parasites. Let's begin with viruses. Viruses are among the most dangerous infections that we, as a species, have to deal with. Unlike other microbes that are typically spread by vermin or insects, viruses can spread directly from human to human through a sneeze or a cough. Smallpox killed some 500 million people last century, and influenza another 100 million in the 1918 outbreak alone. Now, with overpopulated cities where people are in close proximity, and given the ease of international travel, a single major viral pandemic would be much worse. According to the Centers for Disease Control, if another major influenza pandemic were to occur today, estimates are for 1 billion dead. While researchers work furiously to develop antiviral drugs, a truly effective broad-spectrum antiviral medication still eludes them. But we don't need to look to the apocalyptic to see the effects of viruses. Viruses are vastly underestimated as a cause of chronic disease today. It's not just the millions who currently suffer from viral infections, such as hepatitis C, AIDS, and herpes that are affected, but the average man and woman on the street. Everyone, without exception, is infected with the Epstein-Barr, cytomegalovirus, and herpes viruses. Most people are strong enough to keep these viruses from being much more than a low-grade nuisance, but they slowly eat away at our vitality, taking advantage of us when we are tired or under the weather. They are among the many opportunistic infections that wait for us to let our guard down. What is also generally unknown is that many of the conditions currently considered to be genetic in nature are in fact viral in origin. How does this mix-up happen? Firstly, viral infections are virtually impossible to detect, so unless you know exactly what you are looking for, you are likely to miss them. Secondly, viral infections also have the ability to cause genetic mutations in our DNA. Thus, in some cases, the genetic mutation that a scientist points to as the cause of a disease is actually the result of a virus he cannot detect. Many people today who are told that they have incurable genetic diseases actually have very curable viral infections. If you are dealing with a disease of unknown or genetic origin, or are just feeling run down, odds are you're dealing with a virus. Even though modern medicine has yet to come up with a truly effective broad-spectrum antiviral medication, there is a natural way to directly attack viruses. First, you need to understand a little bit about how viruses work. Unlike all other life forms, viruses are unable to reproduce on their own. Viruses reproduce by commandeering the machinery of our own cells, turning them into virus-making machines. Our own cells end up making the very viruses that can make us even sicker. While this is a very clever strategy for the virus, it does have one exploitable weakness. In order for a virus to reproduce and make us sick, it must first enter our cells. As long as it stays outside our cells, it can't hurt us. This is where we should focus. How can we keep a virus from entering our cells in the first place? It turns out that many viruses use an enzyme called integrase to get inside of our cells. If we can inhibit the integrase enzyme, then many viruses won't be able to get inside our cells to reproduce. Now, back to our friend the raspberry. Ellagic acid, a compound made from raspberries, does just what we are looking for in our fight against viruses. Ellagic acid is an integrase inhibitor. If we take ellagic acid, we will be able to inhibit many viruses, known and unknown, from entering our cells and reproducing. Now let's turn our attention to bacteria. The antibiotic revolution made once feared diseases like tuberculosis, staph, and strep manageable and often curable. Well, at least they used to be. Massive overuse of antibiotics in hospitals and in livestock management has given rise to the superbug. The superbug is antibiotic resistant and very aggressive. The very bacteria we once thought we had beaten are now making a comeback and threatening to wreak havoc around the globe. Right now, 2 billion people in the world, or roughly a third of the world's population, have tuberculosis, and antibiotic-resistant staph and strep run unchecked through our hospitals, often infecting and sometimes killing patients who come in for routine operations. This is understandable. Bacteria reproduce so quickly and mutate so easily that developing resistance to any particular antibiotic drug was only ever just a matter of time. What we need is a way to stop all bacteria, not just one type or another. Moreover, we need to find a way to stop bacteria at a level that they cannot mutate around. The deepest level of any life form is its DNA. Is there a way to affect bacterial DNA without harming ourselves? It turns out that there is. Bacteria, like most life forms, coil their DNA molecule into a very tight ball. This coiling is required to fit the sometimes 10-foot-long DNA strand into a tiny bacterial cell. That's right, DNA can be up to 10 feet long, and it has to fit in a cell 30 million times smaller than its length. Now, what would happen if we were able to uncoil that DNA strand? What if we could pull on it like the loose string on a knitted sweater? You guessed it, the whole coil would unravel. When the DNA is coiled up, the information is accessible, but in an uncoiled state, the DNA would be unreadable. In this state, the bacteria wouldn't have the information required to run its basic life processes. In other words, the bacteria would die. Here's an analogy to illustrate how this works. Imagine that you want to build your first house by yourself. Having never done this before, you decide to go to the library to get some books on basic carpentry and architecture. Unfortunately, when you get there, you find that a minor earthquake has knocked all the books off the shelves into a disorganized mess on the floor. You know that somewhere in that mess are the books you need, but it would take months to find them. It's the same when you unspool the DNA of a bacterial cell. The information, in this case the DNA, is still there, but it is inaccessible, and the bacteria dies, unable to get the instruction on how to accomplish this task. Ah, the humble raspberry. It saves us again. That same ellagic acid compound we get from the raspberry that keeps the viruses from entering our cells also causes the DNA of bacteria to unspool. It turns out that all bacteria use an enzyme called gyrase to keep their DNA coiled, and ellagic acid inhibits this enzyme. Unlike antibiotics that